Hello students, welcome to the channel Chemistry is Fun. In today's video, we're going to learn about how to calculate the lone pairs in the central atom. Usually, lone pairs we observe in the inorganic molecules. Okay, in organic compounds, generally the central atom is carbon. Carbon has no lone pairs, so we mainly calculate the lone pairs in the inorganic chemistry. Okay, so first of all, let us see what are lone pairs and its importance. Lone pair electrons are those electrons which are present in the valence shell of an atom but do not participate in the bonding. So, to understand this, let us take an example of nitrogen. Nitrogen's atomic number is equal to 7. It belongs to 5th A group family or 15th group family, or you can say Nicogens is the general name given to this family. Okay, now when you write the electronic configuration of nitrogen, it is 1s2, 2s2, 2p3. I'll represent the valence configuration with arrow form. Okay, so this is the arrow representation for the valence electrons. Now these three unpaired electrons will usually involve in the bonding with other atoms. Now such electrons which are shared among the other atoms are said to be bond pair electrons. Now this is of our interest, which is 2s2. That is the pair of electron present in the valence shell but do not participate in the bonding. They do not involve in the bonding. Such pair of electrons are called lone pair of electrons. Similarly, you come across lone pairs in 5th A group, 1 pair. 6th A group, you get 2 lone pairs. And 7th A group, you get 3 lone pairs of electrons. Now, how to calculate this in a central atom? What is the importance of it? So, lone pairs are usually they decide the shape or geometry of the molecule. For example, in case of ammonia, we have learned the methods to calculate the hybridization in the previous videos. So in nitrogen, the central atom has got 5 electrons where 3 are bonded with 3 hydrogens and 1 is the lone pair. So altogether there are 3 bond pairs plus 1 lone pair. Together we get the number equal to 4. When the number of hybridization is equal to 4, the hybridization is sp3. In case of ammonia, nitrogen central atom, hybridization is observed to be sp3. So, the expected geometry is tetrahedral and the expected bond angle is 109 degrees 28 minutes. But in case of ammonia, the geometry that is observed is equal to pyramidal shape. Okay, and the bond angle is 107 degrees. So the deviation in the geometry and the bond angle is because of the lone pair, one lone pair that is involved in the molecule. How? When you look at the structure, this is the lone pair, these are the bond pairs. So the lone pairs have greater effect. They occupy a larger space. They repel with these bond pairs. They repel with these bond pairs. As a result, the bond pairs come close to each other and the bond angle between the bonds also decreases. Accordingly, from tetrahedral geometry, now they have become pyramidal shape. So this is the effect of lone pairs in the central atom. So as we have seen the definition and the importance of lone pairs, let us now look at how to calculate the lone pairs with a formula. So the number of lone pairs in a given molecule can be calculated by group number G minus sigma plus pi bonds by 2. Okay, what is the formula? Number of lone pairs is equal to group number minus sigma plus pi by 2. So we'll look at the same very same example, that is ammonia. We don't know how many lone pairs are present in ammonia. Nitrogen belongs to, as we have discussed, it is belonging to 5th A group. Minus, what are the number of sigma bonds in nitrogen? This is 1, this is 2 and this is 3. So there are 3 sigma bonds and you find no pi bonded electrons in the molecule. So it is 0 by 2. So it is 5 minus 3 by 2. How much is it? 5 minus 3 by 2, which is equal to 1 lone pair. 5 minus 3 is 2, 2 by 2 is 1 lone pair. So in ammonia you find 1 lone pair in the central atom. Let us look at few more examples like this. Let's take XeF3 plus ion. Okay, Xa is xenon, which is our central atom. It belongs to 8th A group. It's an inert gas. It belongs to 8th A group. So inert gases usually they do not combine with any other element, but except helium reacts with the fluorine and oxygen, which are the most electronegative atoms. Okay, likewise it forms fluorides, oxides, oxyfluorides, etc. So let us look at the number of lone pairs in this. I am representing this as n. Group number of xenon is 8 minus. Fluorines always bond with other atoms only by a single bond. That means they are monovalent. And whenever there is a single bond, that has to be a sigma bond. So the number of sigma bonds are equal to 3. Okay. Okay, so for the xenon, group number is equal to 8 minus 3 is the bond pairs, plus you find no lone pairs, 0 by 2. Now this is 5 by 2. You cannot have a lone pair in a fractional value. Where did we go wrong? Here there is a positive charge. Okay, you need to remove one electron from this. So instead of 8, here it has to be 7. Now you'll get the correct number. 7 minus 3 is 4 by 2, which is equal to 2 lone pairs. So that means in case of neutral atom or a neutral molecule, you have to consider group number as it is. But in case of cation, you have to do group number minus the charge of the cation. If there is plus 1 charge, you need to remove 1. If there is plus 2 charge, you need to remove 2 from that, as we did in the case of XeF3. Similarly, if you find any negatively charged particle, for example, if we have Bf4 minus, okay, so the central atom is boron. Number of lone pairs is equal to boron's group number is 3. But here, since there is negative charge on the molecule, you need to add 1. So 3 plus 1 will be 4. Now, that from that number you need to remove what are the number of bond pairs? 4, or sigma bonds is equal to 4, and you find no lone pairs by 2. So 4 minus 4 is 0. So you get 0 lone pairs. That means boron has no lone pairs on the central atom. This way you can calculate the lone pairs in any given molecule. Let us look at one more example, which is BrF5. Okay, one more example is BrF5. So bromine is a halogen. It belongs to 7th A group. So number of lone pairs is equal to 7th A group, 7 electrons minus 5 fluorines. Wherever you find fluorine, chlorine, bromine, iodine, you have to consider them as monovalent atoms. So the number of sigma bonds is equal to 5 plus, and you find no pi bonds, so equal to 0 by 2. So 7 minus 2 is 2 by 2, which is equal to 1 lone pair. So bromine in BrF5 is is having 1 lone pair. So number of lone pairs cannot be fixed in every molecule. It varies according to the number of bonds the central atom is undergoing. So this is a simple method to find out the lone pairs in the case of inorganic molecules. Okay, so hope this video is useful. Thank you.